Hey there folks, and welcome back. In this lesson, we're going to be covering a really cool topic, directional derivatives. This is something that traditionally students find to be a little bit challenging when they first see it. But don't worry, this topic is beautiful, very interesting, and with a bit of practice, you'll find that it's really not so tough. In order to begin our discussion, I'd like you to cast your mind back to our lesson on partial derivatives. There, we said that if we have some surface, the graph of a function z equals f of xy, as well as a point on that surface, AB, we can ask for the rate of change of our function as we move away from that point. But of course, we have to specify the direction in which we're moving. We have infinitely many choices. If we move from AB in the direction of the positive x-axis, then we're calculating the slope of this tangent line here. That's the partial derivative with respect to x at AB. Alternatively, if we move from AB in the direction of the positive y-axis, then we're calculating the slope of this tangent line. That's the partial derivative with respect to y at AB. We can actually phrase this in terms of vectors, right? If we stand at AB and move in the direction of 1, 0, well then we're stepping in the direction of the positive x-axis. If instead we move in the direction of 0, 1, then we're moving with the positive y-axis. But what if we wanted to move in a completely different direction? Maybe we want to know the rate of change of our function as we move from AB in this direction, the direction of the vector u. U has components u1 and u2, and since we're only interested in the direction right now, the length of this vector doesn't really matter. We're going to assume that our vector has length 1. By asking for the rate of change of our function in the direction of this unit vector u, we're really asking for the slope of this tangent line here, the tangent line to our surface at AB, and moving with the vector u. This gives us an entirely new rate of change, an entirely new derivative. And while I guess we could call it a partial derivative, we give it its own name. We call it a directional derivative. Our directional derivative is denoted by capital D sub u vector f at AB, the directional derivative of f in the direction of u at the point AB. Just like for partial derivatives, we can write down a limit definition for this derivative. We would be looking for the limit as h goes to 0 of the average rate of change of our function as we move in this direction. Well, let's think about this. To move from AB in the direction of u, we have to change our x component by some multiple of u1 and change our y component by some multiple of u2. So inside our limit, we get f of a plus u1h, b plus u2h, right? So x is moving with u1, y is moving with u2, minus f of ab, all divided by h. As a quick sanity check, what happens when we use the vector 1, 0 for our vector u? Well, in that case, our first term, a plus u1h, is simply going to be a plus h. And our second term, b plus u2h, is simply b. That'll give us the limit definition for the partial derivative with respect to x. And that's exactly what we'd expect to get. It would be the rate of change along this tangent line here. Now, I know what you're thinking. You're looking at this limit and you're thinking, gosh, this looks terrible. And I agree. Working with this limit in practice is pretty tough. So instead, I'm going to show you a beautiful, elegant way to compute this directional derivative that doesn't use this gross limit definition. All right, folks, on this slide, we're going to derive a really classy formula for evaluating our directional derivative. The argument is a little bit technical, but it's a nice application of our chain rule for paths. So do your best to follow along, but what's really important is the formula at the end. At the moment, the only thing we have to work with is our limit definition of the directional derivative, which I've written for you again here. Notice, however, that I can clean up this gross expression by defining a new function. I'm going to define the function g of h to be f of a plus u1h, b plus u2h. That's exactly what you see here. And this expression, f of ab, is exactly what you would get by plugging in 0. So I can rewrite my limit as the limit as h goes to 0 of g of h minus g of 0 divided by h minus 0. Now, does this limit look familiar? You may remember seeing something like this back in Calc 1. When you computed the derivative of a function g of x at some point x equals a, you would have looked at the limit as x goes to a of g of x minus g of a divided by x minus a. Well, that's exactly what we have here, except instead of x, we have h, and instead of a, we have 0. So this expression here is the regular derivative of g with respect to h evaluated at h equals 0. That's step one of our argument. We've rewritten this directional derivative of f in terms of a regular derivative of some other function evaluated at 0. Now let's think about how we might go about computing this derivative. We know that g of h is f of a plus u1h, b plus u2h. Notice that this is a function with two variables, both of which depend on h. So why don't we give these variables some names? We're going to call this first expression x. It's a function of h, so x of h is a plus u1h. This second expression we're going to call y. Y is a function of h as well, so we'll write y of h equals b plus u2h. What we have here is a function f with two intermediate variables, x and y, and one independent variable h. That gives us one of them there tree diagrams. Looks something like this. What we're trying to do is calculate the derivative of this thing with respect to h and plug in 0. Well, according to our chain rule for paths, we can do that by following various branches down from f to h. We get the partial derivative of f with respect to x times dx by dh, plus the partial derivative of f with respect to y times dy by dh. And of course, we're evaluating this whole thing when h is equal to 0. Okay, now can we evaluate some of these derivatives? I think we probably can. Notice that dx by dh is really just this constant u1, whereas dy by dh is this constant u2. Now we have to plug in h equals 0 to this expression. Well, when h is 0, our function x of h is really just a, and our function y of h is really just b. So essentially we're plugging in the point a, b. What we end up with is the partial derivative of f with respect to x at a, b times this u1 term, plus partial f by partial y at a, b times this u2 term. Okay, at this point, folks, we have to take a step back and appreciate what we've just done. We've taken this expression, this gross limit for our directional derivative, and we've rewritten it in terms of quantities that we know. We know how to compute these partial derivatives, and we're given the constants u1 and u2. If we combine the partial derivatives and the components of u in this way, we get the directional derivative of f in the direction of u at a, b. Now, I think this argument is pretty cute, but what's important here is that you're able to apply this result in practice. So check out the following video where I walk you through some examples.